How does more imagery work in EEG BCIs? Have you ever wondered how your brain can control devices without any physical movement? The answer lies in motor imagery within electroencephalography-based brain-computer interfaces. Motor imagery involves imagining specific movements without actually performing them. When you think about moving your left or right hand, your brain generates unique activity patterns, especially in the motor cortex. This brain activity can be detected using electroencephalography, a method that captures electrical signals from the scalp. The key signals to focus on are changes in sensorimotor rhythms. These rhythms include the mu frequency band, which ranges from 7 to 13 Hz, and the beta frequency band, which spans from 13 to 30 Hz. When you imagine a movement, these rhythms can either synchronize or desynchronize, creating noticeable changes that depend on which side of the body you are imagining moving. Electroencephalography-based brain-computer interfaces detect these changes and convert them into commands for external devices. This means you can control devices without any muscle movement. To make sense of these brain signals, brain-computer interfaces use signal processing and machine learning algorithms. Traditional methods often utilize the common spatial pattern algorithm to extract features related to the imagined movement. These features are then classified by machine learning models to differentiate between various motor imagery tasks. Recently, more advanced techniques like convolutional neural networks and long short-term memory networks have been introduced. These methods automatically extract complex features, which improves the accuracy of classification. However, there are still challenges to overcome. The low signal-to-noise ratio of electroencephalography can make it difficult to interpret signals. Additionally, individual differences and overlapping features from different imagined movements can complicate the process. To tackle these issues, researchers are developing hybrid models that combine deep learning with attention mechanisms and support vector machines. This approach helps improve feature discrimination and classification performance. Motor imagery in electroencephalography-based brain-computer interfaces has practical applications, especially in neurorehabilitation. For instance, stroke patients can use these systems to regain motor function by controlling assistive devices or prosthetics with their thoughts. It also offers communication options for individuals with severe motor impairments, allowing them to bypass traditional muscle-based methods. In essence, motor imagery works in electroencephalography-based brain-computer interfaces by detecting and decoding brain activity patterns created during the mental simulation of movement. These patterns are processed through advanced algorithms, enabling direct communication between the brain and devices. This technology holds promise for medical rehabilitation and improving human-computer interaction.